In this video, I will teach you how to perform basic integration. I'll show you basic rules. We are going to work with some powers, some trigonometry. We are going to work on examples which are close to what you can find in the table of integrals. If you don't know what I am talking about when I say the rules of integration or when I mention table of integrals, this video is for you. So let's start with solving some integrals. We have this integral on the paper which we are now going to solve. In order to tackle this problem, I first have to tell you what I mean by integration. You have already learned differentiation. If you have, for example, x squared and you want to differentiate it, basically take its derivative. And by taking its derivative, I mean calculating d over dx of x squared. That is going to give us 2x. We are going to take the derivative of the function x squared, and this dx here means that we are going to take that derivative respectful of the variable x. By doing this, we get that answer is 2x. Integration would be a process reverse of differentiation. So integration is the opposite of taking the derivative. So if a function gives us a certain derivative when we differentiate it, an integration of that derivative would take us back to the original function. So we are essentially integrating a derivative of some function that we want to find. If we take the function 2x, which we got as a derivative, by integrating it, taking the integral of 2x dx, and that is going to give us the result of x squared plus c. So that is x squared plus c, what we get. The way to read this is an integral of 2x with respect to x, or antiderivative of 2x with respect to x. The x here is the differential. The differential gives us an information that x is a variable of integration that we are integrating with respect of x, and not some other variable. And in a few moments, I will explain to you what this plus c means. Let's take a look at the problem which we had started from. We are integrating a derivative of some other function that we are going to find, and that function is called an antiderivative or indefinite integral. For a polynomial like this one, where we have a bunch of terms added and subtracted, we can integrate each term one by one and then put them together in a string for a full integral. For integrating this, we need to know the power rule. So the power rule, which I am referring to, states that an integral of x to the power n dx is going to give us the result of x to the power of n plus 1 divided by n plus 1 and plus c, where this c is some random variable from the set of R, the set of real numbers. In order for us to be able to apply this rule, n has to be different than negative 1. Note here that you can't divide with 0, so if n is equal to negative 1, you have a division by 0. As you can see in our integral, the first term that we have is x cubed. It has a power, so we can use a power rule. The power rule states that if your power is not negative 1, the integral of x to the power is x to the power raised by 1 over that power raised by 1 and plus a constant c. For x cubed, an integral of that would be x to the power of 3 plus 1 divided by 3 plus 1 and plus some constant c. Basically, this means that an integral of x to the fourth power dx is x to the fourth x of the third power is x to the fourth power divided by 4. So when solving this integral, the first term of the solution is x to the fourth power divided by 4. Now we get to this minus sign over here. We can keep the subtraction because of sum and difference rules, and this term has x squared. So x to the second power, but it also has this number 6 in front in multiplication. Anytime that you have a constant multiplied by something where that constant is in front, like it is here, you can keep the constant and then integrate the rest. So we are going to keep 6 and then integrate x squared using a power rule. Now to integrate x squared, we know that the integral of x squared dx by using the power rule here is x to the power of 2 plus 1 divided by 2 plus 1 and plus some constant c. This is x cubed divided by 3 plus c. And this x cubed divided by 3 I am going to plug here as a term of our solution. This addition here we are going to keep. It's the sum and difference rule. The next term is x. X is the same thing as x to the power 1. So using the power rule here, x raised to the power 1, we get that this is x squared divided by 2. And finally we have come to this constant here plus 1. Every time you have a constant term, the integral of that will be the constant multiplied by a variable x in this case. So we have plus 1 multiplied by x. I want to show you another rule. It states that an integral of k multiplied by dx is equal to kx plus c, where this k is a real number, a constant. This is a constant rule. You can think of it as a separate rule, or you can think of it as a power rule. You can represent constant number 1 as 1 multiplied by x to the power 0. Well then, when you integrate this 1 multiplied by x to the power 0 dx, you get x to the power of 0 plus 1 divided by 0 plus 1, and plus that constant c. So this is just x to the power 1 divided by 1 plus c, which is x plus c. It really doesn't matter how you look at it. The integral of 1 is 1 multiplied by x, which is x. Also, if you see something like this, an integral of dx, there is an implied 1 there, so there is a constant rule. The integral of dx is just x plus c. As you have noticed by now, all of these integration rules are similar to derivation rules. That is because they are opposite to one another. You can pretty much inverse a lot of derivative rules to get integration rules, but just be careful as not all of them are similar and have a counterpart. There is no product rule and there is no quotient rule for integration. We are not done here with this calculation. We have to add plus c at the end, where this c is a real number. This is very important. We don't know if there was a number at that position originally, and if so, what it was. That is why we put plus c as a placeholder, and it represents all possible antiderivatives. Mathematically speaking, if we have some function f of x, f is capital, and we take its derivative, we get the function f of x, f of the lowercase. So the process of the derivation gave us one specific function. But take a look at the function f of x plus 5 and take its derivative. That is just f prime of x, as the derivative of any constant is 0. So this is just f of x. The integration works opposite of the derivative. So when you take an integral of the function f of x dx, the lowercase f, respectful of the variable x, this is an entire family of functions. It contains all the functions that have as a derivative this function here, f of x, f in lowercase. This family of functions has an element f of x where that f is capital. And it also contains a function f of x plus 1 and the function f of x plus 5 and any other number that you can think of, the real number. So this integral of the f of x dx is really a collection of all the functions that have for a derivative this function f of x. So the functions that look like f of x plus c, where c is any real number. And here in our example, the integral of x cubed minus 6x squared plus x plus 1 dx, as a result we got x to the 4th power divided by 4 minus 6x cubed divided by 3 plus x squared divided by 2 plus x and plus that c, where c is any real number. So this here is a family of functions because this here is a family of functions. So this is a collection of all the original functions, higher level functions we got by integrating. If you want, you can check this answer by taking its derivative and you will get as a result the original integrand. It doesn't matter that there is this plus c at the end because the derivative of a constant is just 0. You can now ask a legitimate question. Why didn't I put plus c on every term as I went along integrating? It's because it doesn't matter at the end. You are just going to add up adding a bunch of real numbers together and the result of that is a real number. The question now is what happens with other kinds of powers. Let's first do some negative powers like the integral of x to the power of negative 3 dx and an integral of 1 over x squared dx. So let's solve these two integrals. Remember that the first thing that we have to do is to determine what is the area in which this integral is defined. So x to the power negative 3 is just 1 over x cubed. That is the algebra part that you have to know in order to do calculus. And as you can see, we have this x cubed in the denominator of a fraction. That means that x cubed has to be different than 0 as division by 0 is not allowed. Therefore, x has to be different than 0. That is going to give us the area in which this integral is defined to be an entire set of real numbers except the number 0. So you can write this as from negative infinity to 0 interval, union the interval from 0 to positive infinity where this 0 is not included. Now that we have an area in which the integral is defined, we can focus on solving the integral. In this integral, we have a negative power x to be raised to the power of negative 3. Here also we can use a power rule. We can use a power rule as long as that power is not negative 1. So this integral is going to be x raised to the power of minus 3 plus 1 divided by minus 3 plus 1 and plus that arbitrary constant c at the end of the integration. So this is just x to the power negative 2 divided by negative 2 plus c, and that is going to give us the result of negative 1 over 2x squared plus c, where that c is any real number. This second integral that we have, we are going to solve in the same manner. We have x squared in the denominator, so x squared has to be different than 0, and that means that x has to be different than 0. The area in which this integral is defined is again the set of all real numbers except the number 0. Let's integrate this. This is the same as x to the power of negative 2 dx, and when we use a power rule, this is x to the power of negative 2 plus 1 divided by negative 2 plus 1 and plus c. The final result we get is negative 1 over x plus c, where that c is an arbitrary real number. You can observe the pattern here, which is if you can rewrite as a power up top in the numerator, do that. Then integrate using a power rule and finally simplify. The most important thing to keep in mind here when using the power rule is that exact statement of the power rule. Integral of x to the power n dx is x to the power of n plus 1 divided by n plus 1 and plus c, and you have to remember then that n, the power, has to be different than a negative 1. This is crucial, so keep this power rule in mind always. Let's observe the integral of x to the power negative 1 dx. You can't use a power rule here because if you take a look in a table of integrals, there is a separate rule for this. And that separate rule is that the integral of x to the power negative 1 dx is ln of the absolute value of x plus c, where that c is a real number. This ln is a log for a base which is a natural number e, that Euler's number. You should know by heart that entire table of integrals, but I want to make a little note here. This is not actually ln of the absolute value of x plus c. It's more like that an integral of x to the power negative 1 dx branches out into two cases, ln of x plus c, where x is larger than 0, and ln of negative x plus some different constant. Let's call this constant c1, and this constant here c2 for x smaller than 0. C1 and C2 are any two real numbers. They don't have to be equal in a general case. We just use this simplified notation here, but it actually has these two cases in it. So keep in mind that you are dealing with two cases simply written in this one notation. I will make a separate video on that topic, and I will name it How Your Math Professor Lied to You, and I will put a link to it here in the description when I finish that video. So subscribe to the channel just to get notified when I make some new videos, as there is more interesting stuff coming up in the future. Let's observe now this example. Integral of 1 over 4x dx. Again, 4x is in the denominator of this integral, so it has to be different than 0, and that means that x has to be different than 0. The area in which this integral is defined now is the set of all real numbers excluding the number 0. Let's solve this integral now. We have this constant 1 over 4, and that can go in front of the sign of an integral. So this is 1 over 4 integral of 1 over x dx, and that can be transformed into 1 over 4 integral of x to the power negative 1 dx. This integral is easy to solve, and we already know what it is from the table of integrals. It is 1 over 4 ln of the absolute value of x, and finally plus that arbitrary constant c, which is a real number. A rule that I want you to keep in mind is that an integral is a linear function. So if you have an integral of af of x plus bf of bg of x dx, this is equal to a integrals of f of x dx plus b integrals of g of x dx. This is the rule of linearity of an integral operator. These numbers a and b here are real numbers, they are real constants. And of course, when you use this rule, when you get these two integrals on the right side of the equation, well, now you just have to focus on solving these two integrals. So here, when I have pulled out this constant 1 over 4 in front of the sign of an integral, this rule of linearity for an integral is the one which I have applied. Now the question is, what happens with fractional powers? How are we going to solve an integral of x to the power of 2/3 dx? Now we can ask the same question. How do we solve an integral of 1 over x square root of x dx? Or how do we solve an integral of a square root of x dx? There is also a square root of x cubed dx, and finally an integral of the cubic root of x squared dx. Let's attempt to solve the first integral of this list, integral of x to the power of 2/3 dx. As you can see, x to the power of 2 over 3 is defined for every x which is a real number, and that means that the area in which this integral is defined is an entire set of real numbers. 2 over 3 is a fraction which is different than number -1, so we can use the power rule. So this is x to the power of 2/3 plus 1 divided by 2/3 plus 1 and plus that famous constant c. So this is just x to the power of 5/3 divided by 5/3 plus c, and that is 3 over 5, a cubic root of x to the 5th power, and plus c. This c is a real number. The next integral on our list, integral of 1 over x square root of x dx. Let's first find what is the area in which this integral is defined. Here in the denominator we have x square root of x. In order for this integral to be well defined, well, this expression x square root of x has to be different than 0, and in order for this square root function to be well defined, also x has to be larger or equal to 0. So from this first condition, we can deduce that x has to be different than 0, and we have that x is larger or equal to 0 as our second condition. Basically, x is different than 0 and x is larger or equal to 0. That means that x is strictly larger than 0. So area in which this integral is defined is a set from 0 to positive infinity. This is an open interval from 0 to positive infinity. It does not include this number 0. So let's now solve this integral which we have started from. We can transform this integral. So we have 1 over x, and the square root of x is just x to the power of 1/2 dx. So this is an integral of 1 over x to the power of 1 plus 1/2 dx, and that is just an integral of 1 over x to the power 3 over 2 dx. Well, this is an integral of x to the power -3/2 dx, and we can apply the power rule at this step. So we get x to the power of -3/2 plus 1 divided by -3/2 plus 1 and plus that arbitrary constant c. So when we simplify all of this, we get that final solution is -2 multiplied by 1 over a square root of x and plus that c, where c is a real number. Let's now solve the next integral on our list, the square root of x dx. For this integral to be well defined, a square root function which we have here in the integrand has to be well defined. And the square root function is well defined for x's which are larger or equal to 0. So the area in which this integral is defined is a set from 0 to positive infinity. Of course, this interval contains the number 0. So this is our area where the integral is defined. And we can transform this square root of x when we are trying to solve the integral into x to the power of 1/2 dx. And from this point, we can just apply the simple power rule. So this is x to the power 1/2 plus 1 divided by 1/2 plus 1 and plus that constant c. So finally we get that this is x to the power of 3/2 divided by 3/2 plus c, and that is just 2/3 cubic root of x squared and plus c. This c is of course a real number. The next integral which we have on our list is an integral of a square root of x cubed dx. Now this integral is well defined only when a square root function is well defined, and that means that x cubed has to be larger or equal to 0. Therefore x has to be larger or equal to 0, and that means that the area in which this integral is well defined is an interval from 0 to positive infinity, which includes number 0 in it. So this integral is then equal to an integral of x to the power 3/2 dx, and at this point we can just apply the simple power rule. So this is x to the power of 3/2 plus 1 divided by 3/2 plus 1 and plus that constant c. This is x to the power of 5/2 divided by 5/2 plus c, and that is 2/5 square root of x to the 5th power and plus c, where this c is a real number. Let's solve the integral of a cubic root of x squared dx. Now, in order for this integral to be well defined, a cubic root of x squared has to be well defined, and that function is well defined in an entire set of real numbers. So that is the area in which this integral is defined. This can be algebraically transformed into x to the power of 3/2 dx, x to the power of 2/3 dx. I have a cubic root here, and we can apply the power rule here. So this is x to the power 2/3 plus 1 divided by 2/3 plus 1 and plus that famous constant c. So this is x to the power of 5/3 divided by 5/3 plus c. So this is 3/5 cubic root of x to the 5th power and plus c. This c is again a real number. At this point, I want to show you how you can solve integrals which are even more complicated than ones which we have seen so far. So let's observe this integral. For this integral to be well defined, a square root of x has to be different than 0, as that is in the denominator of a fraction, and in order to be well defined this square root function, x has to be larger or equal to 0. So that means that x is different than 0 and x is larger or equal to 0, and that means that x is strictly larger than 0. So the area in which this integral is defined is an open interval from 0 to positive infinity. Now, to solve the integral, the question is how to tackle this problem. The quotient rule for integration does not exist. Remember, the quotient rule for derivation is u over v derivative, that is u derivative multiplied by v plus u multiplied by v derivative divided by v squared. This rule does not exist for integrals. But if you remember, I have told you that integral is a linear operator. So what you can do is to separate everything that you have in the numerator into multiple integrals and tackle them one by one. If you have an idea to integrate numerator and the denominator separately, I want you to immediately forget that heresy, as that is something that is incredibly naive and it simply does not work. I have seen students try that before, but I have to tell you that it doesn't work. Just throw that idea in the garbage where it belongs. Let's use algebra to break this into two fractions. So this integral can be broken into an integral of, and fraction is, x divided by a square root of x plus 6 divided by a square root of x dx. Now we can use that linearity of an integral operator. So this is an integral of x divided by a square root of x dx, plus 6 is a constant, so it can be put in front of the sign of an integral, dx divided by a square root of x. As you can see, these are two integrals which are much simpler to solve than the integral which we have started from. So let's solve them. This is an integral of x to the power of 1 minus 1/2 dx plus 6 integrals of x to the power negative 1/2 dx. This is equal to an integral of x to the power of 1/2 dx plus 6 integrals of x to the power negative 1/2 dx. So this is just equal by using the power rule, x to the power of 1/2 plus 1 divided by 1/2 plus 1 plus 6 multiplied by x to the power negative 1/2 plus 1 divided by negative 1/2 plus 1 and plus famous constant c. So this is equal, just to calculate all of this, x to the power of 3/2 divided by 3/2 plus 6 multiplied by x to the power of 1/2 divided by 1/2 and plus c. So this is 2 over 3, a square root of x cubed, and plus 12 square roots of x plus c. This c is just a real number. Let's now attempt to solve an integral of x plus 1 multiplied by 3x minus 2 dx. Now you can see that this integral is defined on an entire set of real numbers. Let's solve it now. There is no product rule for integration, so the idea is to expand it and see where that is going to get you. Remember, the product rule for derivation was u multiplied by v derivative is u derivative multiplied by v plus u multiplied by v derivative. This rule does not exist for integrals. So that is why we have to find a different path to solve this problem. So when we multiply these two brackets, we get 3x squared, x multiplied by 3x, minus 2x, plus 3x minus 2 dx. Now we see minus 2x plus 3x, that gives us just x. We are going to rewrite everything else, and now we can use that famous linearity of an integral operator. So this is 3x squared dx plus an integral of x dx minus 2 integrals of dx. So this is finally 3 multiplied by x cubed divided by 3 plus x squared divided by 2 minus 2x and plus c. So this is x cubed plus x squared over 2 minus 2x plus c, where c is a real number. The idea is to transform the problem so that it fits the basic integration rule. So far we were talking about power rule, but that is just one of the basic integration rules. Other basic integration rules you can find in the table of basic integration rules. If you look in that table of integrals, you will see trigonometrical integrals. Let's now talk a little bit about those. So let's take for an example an integral of 5 cosine of x plus 4 sine of x dx. In order to determine the domain of this integral, we are going to analyze its integrand. We have a cosine x function, and that is going to be defined for all x's which are real numbers. The sine of x function is defined also for all real numbers x, and these two facts are going to give us the domain of an integral to be an entire set of real numbers. Let's now solve this integral. So this is equal to, we are going to use that linearity of an integrational operator. So this is 5 integrals of cosine x dx plus 4 integrals of sine x dx. In the table of basic integrals, you will recognize these two integrals. So this is going to be equal to 5 multiplied by integral of cosine x dx. In the table, you will see that that is the sine of x. And then we have plus 4 multiplied by the integral of sine x dx. And in the table, you will see that that is the negative cosine of x. And at the end of the integration, we put this plus c for that famous real constant. So this is 5 sine of x minus 4 cosine of x and plus c, where c is a real number. These two integrals are just opposite of corresponding derivatives. So if you have a sine of x derivative, that is going to be a cosine of x. And if you have a cosine of x derivative, that is going to be negative sine of x. Then if you take an integral of this cosine x dx, you will get sine of x plus c. Sine is this sine right here. And let's see what happens with this one. If you take an integral of sine x dx, that will give you just negative cosine of x and plus c. The question is, why does this happen with a minus sign? So if you take a sine of x function and you take its derivative respectful of the x variable, you will get cosine of x. And then if you derive that again respectful of the x variable, you will get negative sine of x. By taking the derivative again, you will get negative cosine of x. And if you attempt to take a derivative one more time respectful of the x variable, you will start here at sine of x. Remember that integration is an opposite operator of a derivative. The sine and cosine derivatives and antiderivatives are cyclical. As you can see here, they repeat in the cycles of 4. So let's see what happens with integration. Let's start again with sine of x. When you integrate this sine of x with the respect of the x variable, that is why you have that dx here, you will get negative cosine of x. And when you take negative cosine of x and you take an integral of that respectful of the x variable, you will get negative sine of x, which you had here. If you take an integral one more time respectful of the x variable, you will get cosine of x. And guess what? If you take that integral again respectful of the x variable, you will return to sine of x. I want to show you some more trig integrals, and I will give them in a table. So an integral of secant squared of x dx is tan of x plus c. the integral of the cosecant squared of x dx is negative cotangent of x plus c. An integral of secant x multiplied by tan of x dx is going to be a secant of x plus c, and an integral of cosecant of x multiplied by cotangent of x dx is going to be negative cosecant of x plus c. For these table integrals, it's easy to look up what they are equal to, and as I have told you previously, you should know this information by heart. If you, on the other hand, encounter something like an integral of tan squared of x plus 1 dx, you are going to use some trig identities. I know that some of you guys have a love-hate relationship with trig identities, so I have decided to make a couple of videos dedicated to lectures and exercises in trigonometry, so that you can learn that as painless as possible. Stay tuned for those videos as they are certainly going to appear on the channel. Trigonometry appears a lot in calculus, and those identities can help you here to rewrite an integral in a more useful form that is easier to integrate. In this integral right here, we are going to use a trigonometrical identity that tan squared of x plus 1 is equal to a secant squared of x. So this integral is by this identity transformed into an integral of secant square of x dx, and as you can see here, that is just tan of x plus c. For an integral of 1 minus cosine squared of x dx, we are just going to use the basic trigonometrical identity that this is an integral of sine squared of x dx. And I have already solved this integral here on the channel in my 100 integrals solved series. So I encourage you to go and attempt to solve some of the integrals from these lists. They are linked here in the description. Let's observe now the integral of sine x divided by 1 minus sine squared of x dx. We can use trigonometry again, and this is transformed into sine of x divided by 1 minus sine squared of x is cosine squared of x dx. And as you can see, we can transform this into sine of x divided by cosine of x multiplied by 1 over cosine of x dx. So this is then going to give us an integral of tan of x multiplied by secant of x dx. And as you know from the table, this is just secant of x plus a constant c. The point that I'm trying to make here is that through these examples, I am demonstrating to you how knowledge of trig identities can make solving these integrals easy. Whereas if you don't know these trig identities, things just become that much harder. Another table integral that you will encounter is an integral of e to the power x dx, and that is e to the power x plus c, where c is a real number. The question is, what are you going to do if your integral is more complicated than the integrals which made their appearance in this video? If you have larger forms, more terms multiplied or divided, or some combination of the three, those integrals you are going to try to solve by various other methods, like integration by parts, the DI method, substitution, partial fractions, or improper integrals. There is also trig substitution. These are just some different techniques which are going to fit your integral into an integration rule. The important question is, how do you know how to approach an integral? So these are all just some of the topics that I'm going to discuss here on the channel, or I have previously discussed. So take a look in my videos and you might find an answer to the question that you may have. I hope that this video has helped you to understand the basics of integration. Please subscribe to the channel as that support helps me a lot. Don't forget to like and share. If you have a specific question or a topic that you want discussed here on the channel, please write about it in the comments.